This time we're going to discuss the three ways to traverse a tree. We call this the three tree traversals. These are the pre-order traversal first, the second is in-order traversal, and the third is post-order traversal. To traverse a tree means to visit all the nodes of the tree, starting from the root of the tree, then down to the interior nodes, and lastly down to all the leaves of the tree. As the tree is traversed, every node that is visited is added into the list of nodes visited. In this way, when the tree traversal is finished, you have created a list of all the tree nodes visited from the first node visited to the last node visited. This is the recursive definition of the three tree traversals. Say the given tree is called T. On the first case, if the tree T is null or it is an empty tree, and that is denoted by this symbol, an empty tree, then the empty list is the pre-order, the in-order, and the post-order list of T nodes. So the pre-order of T is equal to the in-order of T, which is equal to the post-order of T, and that is equal to the empty list, because the given tree T is a null tree. Okay, so we call this a null tree or an empty tree. It has no nodes. The second is when the given tree T is a single node tree, or it consists only of a single node, and that single node is the root of the tree T. So that node by itself is the pre-order, in-order, and post-order list of the nodes. So in the second case, when the tree T is a single node tree, then the pre-order of T, which is equal to the in-order of T, which is equal to the post-order of T, is a list with only one element. Okay, so say if this is the single node tree T with only one node A, and that is the root of the tree T, then the pre-order of T, which is equal to the in-order of T, which is equal to the post order of T, is a list having only one element, and that is the node A. So in the second case, this is a single node list. For the third case, this is for a tree T having more than one node. So say for example that in this tree T, the root is N, and the subtrees are T1, T2 up to Tk. So there are K subtrees. So say this is your tree T under case number 3. Say this is N, the root, and it has K children. So this is the first child N1, the second child N2, and the kth child, okay, the kth child node of the root is denoted as Nk. So under N1 there are subtrees also, and also for Nk. Say for example for N1 there are 3 children, for N2 it has 2 children, and for Nk it has 3 children. So we call this, in this tree T, okay, the whole tree in here, N is the root, and all of these nodes here down to the leaves from N1 down to all the leaves, we call this subtree T1. And from this node N2 down to all the leaves, that is the subtree T2. And from node NK down to all the leaves, that is the subtree TK. So given that N is the root of this tree T, and subtrees are T1, T2 up to Tk, okay, assuming that there are k subtrees. Then how do we get the pre-order list or the pre-order traversal of the nodes of T, the in-order or the in-order traversal, and the post-order list or the list resulting from doing a post-order traversal of the nodes of 3T? How do we get it? Now we have here in 3.1, it describes here how to get the pre-order list of the nodes of the tree, and 3.2 describes how to get the in-order list of the nodes of the tree when we do in-order traversal, and 3.3 describes to us how we are going to obtain the post-order list of all the nodes of the tree T when we do post-order traversal of the tree T. Now let's try to use the same mathematical expression that we have discussed last time. And this is the 4 plus 9 divided by 3 minus 2 times 6. So last time we were able to construct the mathematical or arithmetic expression 3 representation for this mathematical expression. So since this is to be performed first, we construct the subtree to represent this sub-expression. So this is now 9, the left operand, and divide the operator, and the right operand is 3. Now, always remember never to exchange these two. Since in the given, this is the left operand and this is the right operand, then in the subtree or in the tree, 9 should appear as a left child and 3 as a right child. It should be consistent with the given expression. The left operand is a left child and the right operand is a right child of the operator, which is the parent node of these two operands, 9 and 3. And the value of this one is the right operand for this addition operator, and 4 is the left operand. So this would be plus in here, and the left child is 4. And the right child is this sub-expression represented by this sub-tree. And next is minus this one. So for subtraction, which is the operator to be performed last, this sub-expression here is the left operand, and this sub-expression here, 2 times 6, is the right operand. So again, for subtraction operator, the left operand is this whole sub-expression here, and the right operand is this expression here. This whole subtree is the tree representation for this sub-expression, which is the left operand of subtraction, and this sub-expression here is the right operand for the subtraction operator. So this one is the left child, since it is the left operand of minus. We have here minus, and the right child is the operator multiplication, which is the parent node of this operands 2 and 6. So the left operand of multiplication is 2, so it goes here as the left child, and 6 is the right operand of multiplication, so it goes here on the right as the right child of multiplication node. Okay, so this is now the whole mathematical expression tree or the whole arithmetic expression tree representation for the given mathematical expression, which is this. Let us now try to get, with that, let's now try to get the pre-order list of the nodes of this tree. Say, let's denote this as 3T. So this time, let's try to find the pre-order list of all the nodes of 3T when we do pre-order traversal. The sequence of the nodes in the list is the order of the visit. As defined in here, for the pre-order traversal, we start to list the root of the 3T, which is N. And in this case, in our tree here, it is minus. So let's write in here, first node is minus, which is the root of the 3T, and then followed by the nodes of T1 in pre-order. And the T1 in here is this sub 3. This is sub 3 T1, and this is sub 3 T2. So in this 3T, there are only two sub 3s, T1 and T2. So the value of K here is equal to 2. Since under the root, we only have two sub 3s because there are only two children nodes, the plus and the multiplication. So this would be minus the root, list the root first, followed by the pre-order of T1, which is whose node is plus. So let's try to use the name of the node that's plus, and then followed by the pre-order of the nodes of sub 3 T2. Okay, so this is pre-order of T2 is this one, whose root is multiplication. And then bring down minus. Let's find now the pre-order of plus using the same definition here. So for the pre-order of T1, this sub 3, the root is plus, so we list it here, plus, and followed by the pre-order of, in this 3 now, the T1 is this part here. This is your T1. And this part here is your T2. So T1 is the sub 3 whose root is the left child of plus, or the first child of plus. And T2 is the sub 3 whose root is the right child of plus. So we say here plus, and then the pre-order of this one, T1 here is 4. The root of T1 here is 4. And followed by the pre-order of T2, whose root is division. Okay, so this part here is the pre-order of plus. Okay, and then next is to find this one, the pre-order of this 3, sub 3. So that is now, the root is multiplication, and then the pre-order of the T1 here is this one, and the T2 here is this node 6. So T1 and T2 in here, this time, are single node trees. So the root here is multiplication, and then we get the pre-order of that. So we say pre-order of 2, the root of the single node sub 3 T1, okay, this one here, and then followed by the pre-order of that. So we say pre-order of 6. So this one in here is our answer for this part here. So this one again is the pre-order of the sub 3 whose root is asterisk. And then we continue, bring down minus, and then bring down plus, and then find what is the pre-order of 4. 4 is a single node 3. This is a single node 3. And what is the pre-order of a single node 3 from our previous discussion? It is simply the node, that one node. So it is 4. The pre-order of 4 is simply 4. And then the pre-order of division, this one here, the pre-order of that is first the root, which is division, and then followed by the pre-order of 9 and the pre-order of 3. So pre-order of 9 and then followed by the pre-order of 3. So this one here is the pre-order of division, this part here. And then bring down asterisk and then get the pre-order of 2. The pre-order of 2 is, this is a single node tree, so the pre-order is simply the node 2. So this is 2. And the pre-order of 6 is, this is a single node sub-tree, so it is simply 6. So again, the pre-order of 2 being a single node tree is that single node 2, and the pre-order of 6 being a single node tree is that node 6. So let's just write them here, asterisk, and then 2, 6. Okay. And to continue, bring down minus, bring down plus, bring down 4, bring down division. What is the pre-order of 9? Pre-order of 9, this is a single node subtree. So the pre-order of that single node subtree is just the node 9. And the pre-order of 3, this is a single node 3 again, is that single node 3. And then bring down asterisk and bring down 2 and 6. So this time, we have reached the stopping case of recursion. On this part here, we have recursive definitions, like this one, recursive definition for pre-order. Okay, so we get, to get the pre-order of the whole tree, this whole tree here, we need to get the pre-order of the subtrees until there are no more subtrees, but what's in the list would be only the nodes of the tree T. So these are all the nodes of the tree T. So finally, our answer for the pre-order of T is the list containing the nodes in that same order, minus, plus, 4, divide, 9, 3, multiplication, and then 2, and then lastly, 6. So this is the pre-order list of all the nodes of the tree T. That's the sequence or the order of the visit. Now, what have you noticed to the pre-order list of all the nodes of the given mathematical expression tree? This is the same as the prefix form of the mathematical expression. If we're going to get the prefix of this infix form, if we're going to get the prefix form of this infix expression, that would be, first you perform this, so that's divide 9, 3. Then next is this, times 2, 6. And then for addition, the operands are 4 and this one. So it would be 4 as the left operand, this one as the right operand, and the operator is addition. So this is now the prefix form of this sub-expression here. And then this one and this one are the operands of subtraction. And this one is the left operand, this is the right operand, and the operator is subtraction. So we put subtraction at the front of the symbols. And so this is the complete prefix form of the given infix expression. If we're going to check it If we're going to check it, compare it with the pre-order list, take note that they are the same. The pre-order list of all the nodes of a mathematical expression 3 denoted as t is the same as the prefix form of the original mathematical expression. Next, for the in-order list of all the nodes of the 3t, as we do in-order traversal, this is how we create the in-order list. First, you're going to get the in-order of all the nodes of T1. Okay, recall again that your T1 at this point is this one. For node minus, this is the T1, and this part here is the T2. So to get now the in-order list of the nodes of the tree, as we do in order traversal, so to get now the in-order of the nodes of the tree, first we're going to find the in-order of T1, which is this subtree here, T1, whose root is plus, and followed by the root of the tree, T, which is minus, followed by the in order of T2, and the in order of all the subtrees up to the last subtree. But in this case, we only have two subtrees, T1 and T2. So this is the in order of T1, the in order of T2. If there are four subtrees, say for example this is N, and this is N1, N2, N3, and N4, and each are subtrees, then the in order would be first the in order of N1, the subtree whose root is N1, followed by the root N, which is this, the root, followed by the in order of the subtree whose root is N2. Okay, this is your T1, this is your T2, this is your T3, and this is your T4. In this case, K is equal to 4. So you will have in here in order of N2, followed by the in order of N3, and then lastly, the in order of N4. Okay, where this one here is the root. So to continue, what is the in order of T1? This one. By the same definition of in order, so the in order of T1 is the in order of 4, followed by the root, plus the in order of division. So this part now is the in order of T1, and then bring down minus, and the in order of T2, which is this subtree, is first the T1 of this is 2 and the T2 is 6. So we say here in order of 2, the root of the subtree, the single node 3, and then the root is multiplication, and then next is in order of 6. So this part here is the in order T2. Okay, continuing in order of 4. This is now a single node 3. So the in order is simply the node 4. Bring down plus, and the in order of division is the in order of 9, followed by the root, which is division, and then followed by the in order of 3. So this part here is your in order of division. Then bring down minus, and then the in order of 2. This is a single node 3, so it's just 2. Bring down multiplication, the in order of 6. This is again a single node 3, so it is just 6. Then continuing that we bring down 4, bring down plus, the in order of 9. This is a single node 3, so that is simply 9. Bring down division, and in order of 3, a single node sub 3 is 3. and bring down minus and bring down 2 times 6. So this is now the in order of the original given 3t. And what have you noticed to the in order of the mathematical expression 3? It is the same as the infix, right? Infix form of the mathematical expression. So the in order list now is this one, all these nodes. That is the in order list of all the nodes of the 3t. For the post order list of all the nodes of the given 3t, okay, say this is again our 3t. As we do post order traversal of the mathematical tree, this is simply defined as the post order of t is equal to the nodes of t1 in post order. So we say post order of, what is t1 in here? Okay, this is our t1 and this is our t2. So let's say we use again the node, the root of the subtree instead of the subtree name t1. So for t1, post order t1, this is post order t1 and then followed by the post order of t2 up to the post order of tk. And then lastly, you list the root. Okay, so that is the definition for post order list in general. And in our given example, 3t, the post order t1, which is this, okay, let's just try to use the root of that subtree instead of t1. Okay, in our example is equal to 2. That means there are also two subtrees under the root. So t1 here is having the root plus, so let's just use the root. And the post order, the t2 is the root of t2, it is multiplication. So we write here multiplication. And since this is the last subtree, t2, what follows after it is the root, which is the subtraction minus. And then continuing, the post order of plus is, what is the post order of this subtree? It is the post order of this, the post order of 4, followed by the post order of this. So post order of division, and lastly followed by the root of t1, which is plus. So this is the post order of plus, the answer for this part. And then for the post order of multiplication, it is the post order of 2, the post order of 6, and lastly, the root of t2, which is multiplication. So we write here post order of 2 followed by the post order of 6 and then followed by the root, which is multiplication. This whole part here is the post order of multiplication. And after the post order of multiplication, we bring down minus. So we have here minus. Continuing, post order of 4. This is a single node subtree, so it's just 4. And the post order of division is post order of 9. So we write here post order of 9 followed by the post order of 3, and the root of the subtree is division. Okay, so this part here is the post order of division. So again, this is the answer for this one here, post order of division. And then we bring down plus, and then post order of 2 is a single node subtree, so it's just 2. Post order of 6 is a single node subtree, so it is 6. And then bring down multiplication, and then bring down minus. And we continue, bring down 4. Post order of 9 is a single node 3, so it's just 9. The post order of 3, this is again a single node 3, So it's just 3. And then bring down division, bring down plus, bring down 2, 6, multiplication, and subtraction. So notice that we don't have any recursive call to perform post order. So we have reached now the stopping case. And so the result here is the post order of the 3T. So this is now your post order T. And what have you noticed to this answer, to this post order of T? Is it the same as the postfix form of the original mathematical expression? Let's find it out by getting the postfix form. So we start with this one. We say 9, 3 divide. And then next we have 2, 6 multiplication. And for addition, this is the left operand 4 and the right operand is 9 divided by 3. So 4 is the left operand, 9, 3 divide is the right operand, and the operator is plus. Next, for subtraction, the left operand is this whole sub-expression here, which is represented by this sub-expression here. And 2 times 6 is the right operand of subtraction, which is this one here. So this is the left operand, this is the right operand, and the operator is minus. So this is now the postfix form of the infix expression, whose mathematical tree representation is this one. The post order of the mathematical expression 3t is the same as the postfix form of the mathematical expression. This is now the post order list of the 3t, and it is equal to the postfix form of the mathematical expression. The two common 3 search algorithms or 3 traversal algorithms, first is the depth first search and the second is the breadth first search. Let's start first with the depth first search, or the acronym for this is, or in short, this is called DFS, depth first search. This is a 3 search algorithm or 3 traversal algorithm which traverses the tree in a depthward motion. And it starts at the root node and explores as far as possible downwards along each branch and backtracks when it reaches a leaf. Nodes may be listed on the first visit of that node or on the last visit of that node. So these are the two common way of listing a node. You list it on your first visit of that node or you list it on your last visit of that node as you do the depth first search traversal algorithm. So given this tree here where the nodes are labeled with these numbers, when we do depth first search traversal, the list of nodes that tells the order of the visit of the nodes is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? So it's like this. You start with the root, you visit this, so it's listed as the first one. So since this is the one which we first visit, this is our first visit for this node 1, we list it, so we have it here 1. And then as we go down, we encounter 2. That's our first visit of 2, so we list it there. And then next, we encounter 3. This is our first visit of 3, so we list 3 there. After that, we reach 4. This is our first visit of node 4, and we list it there. And then we go back, we backtrack, we go up, and this is our second visit of node 3, and we don't list it in the list. Then we go down. This is our first visit of node 5, so we list it there. Then we go up again, backtrack. This is our third visit of node 3. We don't list it again, so we only list the node on our first visit of that node. Then we go up, and this is our second visit of node 2. And then we reach 6. This is our first time to visit 6, so we list it there. And we go up. This is our third visit of node 2. And we backtrack. We go up to node 2. This is our second visit to node 1. And we go down. This is our first visit of node 7, so we list it here. And we go up. This is our third visit of node 1. And we go down, our first visit of node 8, so we list it there. We go down, this is our first visit of node 9, so we list it there. We go down again, this is our first visit of node 10. Then we backtrack, we go up, this is our second visit for node 9. Then we go down, this is our first visit for node 11. Then we go up, third visit to node 9. We go up, second visit to node 8. We go down. This is our first visit of node 12. We go up. This is our third visit of node 8. And finally, we go up and reach back to the root. And that is our fourth visit of the root. So this is the first, second, third, and the fourth visit of the root. So again, we list the node only on our first visit of that node. For the second, third, and the next visit, we don't list that node anymore. So when we do depth first search traversal algorithm and list the node on our first visit, the order of the nodes would be from 1 up to 12. This is depth first search traversal, listing a node on our first visit. The second tree search algorithm or traversal algorithm we have is the breadth first search, in short called BFS, and this traverses the tree in breadthward motion, visiting all nodes on the same depth level. So it starts with the root and explores all the children nodes on the current depth level prior to moving on to the nodes at the next depth level. So it's like this one, first level, and this is the highest level of the tree. List all the nodes in there, so you have 1. And next depth level is this. So list all the nodes there. We have 2, 3, 4. And then next depth level is this one. So we list the nodes left to right, 5, 6, 7, 8. This is the last depth level. We list the nodes from left to right, so that's 9, 10, 11, and 12. The breadth first search list of all the nodes, or the list of nodes, is 1, 2, and 12. So first 1, next depth level 2, 3, 4. Next depth level, that's 5, 6, 7, 8. Next depth level, that's 9, 10, 11, and 12. Say for example, for this given mathematical expression 3 that we used last time, we're going to do depth first search traversal and list the nodes on our first visit of that node. What would be the list of nodes? So again, in depth first search, you start with the root. This is your first visit of the root. And since this is depth first search first visit of the node, we're going to list the root node minus. And after that, we visit plus. That's our first visit, so we list it here, plus. And then we visit 4. That's our first visit, so we list it there. And then we go backtrack. This is our second visit to plus, so we don't list it. And this is our first visit to division, so we list that. And then our first visit to node 9, we list it here. And then we go up, backtrack. This is our second visit to division, and we don't list it there in the list. And we move down. This is our first visit to 3, so we list 3 here. And we move up. This is our third and last visit of division, so we don't list it. And we move up. This is our last visit to node plus, and we don't list it. We move up. Our second visit is this one for root minus. And then we go down. This is our first visit to multiplication, so we list it. And then we move down. This is our first visit to the node 2, so we list it here. And we move up. This is our second visit, so we don't list it there. We move down. This is our first visit to node 6, so we list it here. And we go up, backtrack. This is our last visit to multiplication. We don't list it. And we finally reach back to the node minus. That's our last visit of minus. And we're done with the depth first search algorithm or traversal algorithm. And we have this list here of all the nodes that we have visited when we do depth first search traversal algorithm and listing the node on our first visit of that node. And what have you noticed to the order of the nodes? It is the same as the prefix form of the mathematical expression. The prefix form, the depth first search traversal algorithm, the resulting list of all the nodes on first visit is the same as the prefix form of the mathematical expression. And of course, from our previous discussion, this is the same also as the pre-order of the tree, T. This is the same. So, our conclusion is that the list of the nodes visited when we do depth first search traversal algorithm listing a node on our first visit is the same as the pre-order list of the nodes of the tree and the same as the prefix form. This time, if we're going to do depth first search traversal, this is DFS last visit. So again, starting in the root, it is not our last visit of this node, so we don't add it in the list. And we go down, visit plus, it is our first visit, so we don't add it into the list. We add only the node in the list on our last visit of that node. So this is not the last visit, so we don't add it into the list. And then we go down, this is our first and last visit of 4, and then we backtrack, we go up, so we add 4 into the list. And then this is our second visit, so we don't add it to the list. This is our first visit, first and last visit, so we add that node into the list. And we go up, this is our second visit, and we go down, this is our first and last visit. Then we go up, so we add 3 into the list. Then we go up, this is our last visit for division, so we list it there. And we go up, this is our last visit for addition, so we add it into the list. And we go up, this is our second visit, it's not the last visit, so we don't add it into the list. First visit, first and last visit, so we add 2 into the list. And we backtrack, we go up, second visit for multiplication, first and last visit for 6, so we add it into the list. And we go up, this is our last visit to multiplication, so we add it into the list. And we go up, finally reach back to the root, and this is our last visit for the root, so we add it into the list. And we are done with our depth first search traversal algorithm. And notice that what we listed here are the nodes visited on our last visit of that nodes. And notice that this is the same as the postfix form of the mathematical expression. And also this is the same as the post order of T, right? If we're going to get the postfix of this, it would be 9, 3 divide, and we have 4, the left operand and the right operand. This is the right operand of plus, and we have 2, 6 multiplication. This is the right operand for subtraction, and the left operand of subtraction is this whole sub-expression here, so we put the minus there. And as you can see, it is the same as the DFS last visit list of all the nodes. So our conclusion is that the depth first search traversal algorithm result when we list the nodes on our last visit of the node is the same as the post order of T and the same as the postfix form of the mathematical expression.